Last up from chapter 16 is number 63. You are standing 2.5 meters directly in front of one of two loudspeakers as shown in the figure. They are 3 meters apart and both are playing a 686 hertz tone in phase. As you begin to walk directly away from the speaker, at what distances from the speaker do you hear a minimum sound intensity? The room temperature is 20 degrees C. So as I said when I introduced interference, this all comes down to path length difference. Let's first deal with the fact that the room temperature is 20 degrees C. That gives us a speed of sound, which is equal to 343 meters per second. And conveniently, the frequency is given to be 686 hertz. And if we recall that V is equal to lambda times F, then lambda is equal to V divided by F, and 343 divided by 686 gives us a wavelength of 0.5 meters. Half a meter. So as I said when I introduced interference problems, they all come down to this notion of path length difference. And if we're walking along up here near speaker 1, I will call this speaker 1, call this speaker 2, the sound has to travel less far from speaker 1 to reach the point of the observer than it does from speaker 2. From speaker 2, it has to travel further. And as we walk along, that path length difference is going to change between the two, and we need to calculate what it is. So I'm going to call the distance that we're walking out here, we're going to call that x. And this distance here is given. And so the distance from speaker 2 is going to be equal to x squared plus y squared. Take the square root. We just need the Pythagorean theorem here. If this is y, is 3 meters. So that means that this distance here, which we will call r2, is equal to x squared plus 3 meters squared. Take the square root of that. And so the path length difference, delta r, is just going to be equal to r2, which is this distance here, minus the distance that the wave has to travel from speaker 1 to the point of the observer. The path length difference is the difference that between the length from this speaker to the observer and this speaker to the observer. And r2 is the length from speaker 2 to the observer, and x is the distance from speaker 1 to the observer. So speaker 2, its wave has to travel a distance delta r further, which is going to be equal to r2 minus x, which is going to be equal to the square root of x squared plus 3 meters squared. 3 meters all squared minus our quantity x. So this is equal to our path length difference, delta r. And the question asks here for a minimum sound intensity, so we care about when delta r is equal to the minimum interference condition, which is going to be m plus 1/2 all times lambda. So we can go ahead and just rewrite this in terms of both of these terms here. This on the left-hand side, we get the square root of x squared plus 3 meters squared is going to be equal to, or minus x, is going to be equal to m plus 1/2 times lambda. And the question asks for what distance is x do we hear this minimum sound intensity. So we need to solve for x, and that is a little bit tricky. But in order to do that, I'm going to go ahead and move this x to the other side. We need to get rid of this square root because it's kind of trapping things right now. So I'm going to move this x to the other side. And on the right-hand side, we get m plus 1/2 times lambda plus x. Now I'll go ahead and square both sides of this equation. And we get x squared plus 9 meters squared is equal to m plus 1/2 times lambda plus x all squared. So algebraically here, I don't see any particularly easy way out of this. I think we just have to FOIL this guy and keep working on it until we get to a value for x. So let me get another piece of paper out here. So let's go ahead and expand this one here. So we just need to multiply it times itself. And so we're going to get on the right-hand side now, we have x squared plus 2 times x times m plus 1/2 times lambda plus m plus 1/2 times lambda squared. And on the right-hand side, we still have x squared plus 9m squared. And so we can see our x squares here cancel. That's convenient. It's going to save us from having to do the quadratic formula, looks like to me. We have a term x remaining here. So we'll keep that on the right-hand side. And we'll move what's left to the left-hand side. So we have 9m squared. And we have minus m plus 1/2 squared times lambda squared, and we have is equal to 2x times m plus 1/2 times lambda. All right, we're looking for x by itself because that's the distance that we want, so we're going to go ahead and divide both sides by 2 times m plus 1/2 times lambda. So then we end up with x is equal to 9m squared minus m plus 1/2 squared times lambda squared divided by 2 times m plus 1/2 times lambda. Well, that wasn't fun, but I think we did it correctly without mistake, so that's good. And now we just need to evaluate this for different values of x. And so we can plug in m equals 0 into this equation and find out what we get for just 1/2 what the value of x is going to be. That gives just 1/2 a cycle difference between that quantity R2 and x. And when we plug in m equals 0 into this equation, we get a value of 17.88 meters. And if we plug in m equals 1, this is going to be 1.5 cycles difference between R2 and that distance x. This gives us a value of 5.62 meters. And when m is equal to 2, we get 2.98 meters. And when m is equal to 3, we get 1.79 meters. So somewhat unintuitively, we are finding that the higher values of m occur closer to the speaker, and that might be unintuitive, but it does in fact make sense because we're going to get a smaller path length difference, meaning closer to the same path length as we get stretched out here pretty far. Then the length of the hypotenuse of this triangle and the distance x are going to approach close to the same value. And so as we get further out, that's going to be the position at which there's less path length difference between the two waves. But when we're in here close, this 3 meters really contributes significantly. And so we have a significant path length difference between the wave that leaves from source 2 and the wave that leaves from source 1. So starting with m equals 3 at 1.79 meters, we're going to have the reason that we started there is because we were given that we started 2.5 meters away. And so the first one that you hit after 2.5 meters is going to be this 2.89 or 2.98 meters that happens when m equals 2. And then you hear the next minimum at 5.62 meters and then 17.88 meters. So there you go. That's how we do our two-dimensional problem. This is probably the hardest two-dimensional problem because we have to find those multiple points of intensity, those multiple points at which the intensity reaches 0. But once again, the clear physics here, the key physics here, is that the path length difference between one source and the other, that is what we want to calculate. And when that path length difference is equal to a full cycle lambda, we get constructive interference. And when it is a half cycle, 1.5, 2.5, then we get destructive interference. Thanks a lot.